All right, so now that you've done your lab, I want to talk about this chart more. I want to explain it and connect it to your lab, and then I want to do an electrochemical cell problem with you. All right, so this chart represents the reduction potentials of metal ions, right? So we start with lithium, and if you connect it to your periodic table, right, top left corner, right, it is in group 1, so it really wants to lose an electron, all right? And it is also very small, one shell outside of the first shell, so it's really close to the nucleus. Lots of pull for electrons from that positive nucleus too, right? So it's got huge pull for electrons, all right? So what that means is a lithium, I got to put my pen back on, a lithium metal really wants to be oxidized, right? It really wants to give up its electron. Real bad, right? And that's why it's at the top of this list, right? This list gives it the worst reduction potential, right? What does that mean? It has the best oxidation potential at 3.00 volts, all right? At positive 3. So it's written in terms of reduction potentials, all right? So as you go down here, things are more and more easily reduced, all right? And that's looking at the substances on the left, all right? If we look on the substances on the left, as you go down, you get things that are more easily reduced. If you flip it, and if you look at it from the perspective of the things on the right, all right, as you go up, these are more easily oxidized. In other words, these are our more reactive metals. And that's what you guys did in the lab, right? As you go up and you look at these metals on the right side, this is their order of reactivity. Lithium is the most reactive metal that we have. I've told you guys I've done experiments with sodium and potassium with water. They will immediately light on fire and start burning and violently burning and dancing around if they come into contact with water, right? That is how ridiculously reactive they are. All right, so lithium, hugely reactive. It really wants to get rid of its electron, right? It really wants to just drop back and be full. So as we look at the right side moving up, these metals are more easily oxidized. As we look at the left side and move down, these ions are more easily reduced, all right? So these are all listed as reduction potentials. Again, remember, to find the oxidation potential, it is the opposite. So we need to use this to do a problem I set up here. So this problem says to represent a voltaic cell involving lead and copper in the following ways. Calculate its potential, write a balanced reaction, and draw it. Oh, and I actually want to add to this too cell notation. Okay. So in order to represent it, draw it, all of these kinds of things, you don't know anything. You have two metals, which is the anode, which is the cathode, right? So we need to figure that out, and you use the potential. The key being that it's talking about a voltaic cell, right? So a voltaic cell means it uses a spontaneous chemical reaction to create electricity, right? To create a current. So we need to figure out which way these two metals combine to make a spontaneous reaction. So let's take the potential for lead, and let's take the potential for, what was it? Copper, off of our chart. And I didn't say copper 2, I said lead 2, but it's copper 2 as well. All right, so let's go back to our chart here. And we used copper 2 recently, so where is it again? There it is. It is 0.34. I'm going to go write it down before I forget. And let's go find zincs. Nope, leads, I mean. There it is. Right here. It is negative 0.13. Okay. So, if we are going to have a spontaneous reaction, we want a positive potential, right? So in this case, if we were to have lead reduced, it would be negative 0.13 as written, and copper therefore oxidized, it would be negative 0.34. So their total would be negative. So that wouldn't be spontaneous. That's what you were looking at the other day. All right, so it does not make sense for lead to be reduced and copper to be oxidized, because then our total potential would be negative. All right, so we have to conclude that this is going to be oxidized and this will be reduced, because we will have an overall positive potential, right? So then the total, I don't know what happened there, my line kind of got squished together, E naught cell will be positive 0.13 and positive 0.34, which is positive 0.47 volts. Okay, so this is our anode, this is our cathode. All right, so that's the first thing you need to figure out. And we've already answered first question. We found the total potential of the cell, 0.47 volts. All right, if we want to write some reactions, then, so this was question 1. We now know that if lead is oxidized, it is going to be lead forming lead ions and giving away 2 electrons, and copper ions plus electrons forming copper. That's the way this is going to work. So in total, we put that together, we can eliminate the electrons. Sorry, not Pb2 positive. Lead plus copper 2 positive forms lead 2 positive plus copper. I don't have a lot of space here, so you know what? I'm going to do number 4 first. I'll do the notation, and then on a new page, I'll visually represent it. So we have anode first, which would be lead, lead ions, copper ions, and copper. Anode, cathode, reactant product, reactant product. Okay, so let's get a new page here, and we will draw it. And I'll outline what's important for me to see when you draw these. Okay, so here's my anode, and here's my lead. Here's my cathode, and here's my copper. Right, so we're going to connect those with a wire. You could put a voltmeter on here to measure it out, and it would read 0.47 like we just calculated. Okay, sometimes if it asks to indicate a voltmeter, that's what you should do. Right, indicate what it would read. And so electrons will go this direction, so you should show that, right, from anode to cathode. You can label this as your anode, this is your cathode. You could label each with a half reaction. I'm going to not be able to show this in a minute, but we could say this is going to be lead, forming lead 2 positive and 2 electrons. This is going to be copper ions plus those 2 electrons, forming more solid copper. All right, so you need to indicate what's in the solution, right? So as I had said the other day, or in the first lesson, it needs to be some sort of soluble salt that involves that metal, right? So the best thing to use would be a nitrate, because they're always soluble. So this could be lead nitrate solution, right, which would be PbNO3 and this could be copper nitrate solution. So there would be copper ions in here and nitrate ions. All right, and we need a salt bridge. So let's that. What color? Let's do it pink. I think that yellow, but that's fine. Right, so my salt bridge allows for ions to flow back and forth between the 2 solutions. Again, something nice like potassium nitrate. All right, allows for the potassium ions to flow one way and the nitrate ions to flow the other to make sure those 2 solutions stay neutral. All right, now the other thing I like to see on here is the actual movement of ions. So if I get something here like the pink, like I meant before, right, I like to see that in this case, because we are oxidizing lead and sending electrons that way, we are sending more lead ions into the solution, right? That's what happens when we're oxidizing. This is breaking down and disappearing. It's losing mass. Over here, we're going to be pulling copper ions from solution, and they're going to be precipitating or plating on this piece of copper metal, and it's going to gain in mass. All right? And so that shows the oxidation and the reduction. I like to see that movement of ions. What else I think is key? Let's just review the salt bridge, right? So if we're adding a whole bunch of positive ions to this solution, the nitrate is going to come this way to balance it. The potassium is going to come this way to balance the fact that we're losing all these positive copper. We'll replace that positive and again keep it neutral. And I think that would be your complete representation. And so yeah, I will list some problems that you can do to practice. Thank you.